Set 2. Example 1. From the first example of the earlier set of solved examples, calculate the gravitational force due to the Earth on Mahendra. Answer. Here, G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Mass of the Earth, M1, is equal to 6 into 10 raised to 24 kilograms. Mass of Mahendra, M2, is equal to 75 kilograms. Small r is equal to the distance between Mahendra and the Earth, which is equal to the radius of the Earth, which is equal to capital R, is equal to 6.4 into 10 raised to 6 meter. The gravitational force due to the Earth on Mahendra is calculated using the formula F is equal to G into M1 into M2 upon R square. Substituting all these values in the formula, we get F is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 into 75 divided by 6.4 into 10 raised to 6 bracket square. Therefore, the gravitational force due to the Earth on Mahendra, F, is equal to 733 newtons. Let us now compare this force with the gravitational force between Mahendra and Virat. Dividing the gravitational force due to the Earth on Mahendra by the gravitational force between Mahendra and Virat, we come to know that the gravitational force due to the Earth on Mahendra is 1.83 into 10 raised to 9 times of the gravitational force between Mahendra and Virat. Example 2. Starting from rest, what will be Mahendra's velocity after 1 second due to the gravitational force of the Earth? Answer. Let us first note down the given information. Here, the initial velocity of Mahendra, U, is 0. The gravitational force on Mahendra, F, is equal to 733 newtons. Mass of Mahendra, M, is equal to 75 kilograms. Time t is equal to 1 second. Let us first find out the acceleration using the formula A is equal to F upon m. Therefore, A is equal to 733 divided by 75. Therefore, A is equal to 9.77 meter per second square. Now, using Newton's first equation of motion, let us find out the velocity after 1 second. The equation is final velocity v is equal to initial velocity u plus acceleration a into time t. Therefore, v is equal to 0 plus 9.77 into 1. Therefore, v is equal to 9.77 meter per second. This velocity is 1.83 into 10 raised to 9 times Mahendra's velocity. Come, let us now proceed to the next part. Gravitational acceleration. The Earth exerts gravitational force on an object near it. According to Newton's second law of motion, a force acting on a body results in its acceleration. Thus, the gravitational force due to the Earth on a body results in its acceleration. This is called acceleration due to gravity, and it is denoted by letter small g. In the previous grade, we have already learned that acceleration is a vector quantity. The direction of acceleration due to gravity is the same as that of the gravitational force of the Earth. it is directed towards the center of the earth, that is, vertically downwards. Let us now calculate the value of G by using Newton's universal law of gravitation and Newton's second law of motion for an object of mass m situated at a distance r from the center of the earth. According to Newton's universal law of gravitation, the gravitational force acting on the object F is equal to universal gravitational constant capital G into mass of the earth, capital M into mass of the object, small m upon distance, small r square. This is equation 1. Now, according to Newton's second equation of motion, the gravitational force on the object F is equal to mass of the object small m into acceleration of the object small g. This is equation 2. From equations 1 and 2, small m into small g is equal to capital G into capital M into small m upon small r square. Therefore, small g is equal to capital G into capital M upon small r square. This is equation 3. If the object is situated on the surface of the earth, then small r is equal to capital R, which is equal to the radius of the earth. Therefore, the value of small g on the surface of earth is equal to capital G into capital M upon capital R square. This is equation 4. Mass of the earth is equal to 6 into 10 raised to 24 kilograms and its radius is equal to 6.4 into 10 raised to 6 meters. Substituting all these values in equation 4, we get small g is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 upon 6.4 into 10 raised to 6 bracket square, which is equal to 9.77 meter per second square. This is equation 5. This acceleration depends only on the mass of the earth, capital M, and its radius, capital R. Therefore, the acceleration due to gravity at a given point on the earth is the same for all objects. This value does not depend on the properties of the object. Suppose the mass of the earth is doubled and its radius is halved of its original value, then what would be the value of small g on the surface of the earth? To find out this value, say g1, we will substitute the value of mass of the earth and the radius of the earth given in the equation g1 is equal to capital G into 2 into capital M upon capital R by 2 bracket square. Rearranging this equation, we get g1 is equal to 2 into 4 into capital G into capital M upon capital R square. Therefore, g1 is equal to 8 into capital G into capital M upon capital R square. Therefore, g1 is equal to 8 into g. Thus, if the mass of the earth is doubled and its radius is halved of its original value, then the value of g is 8 times its original value. Come, let us now study the variation in value of acceleration due to gravity. 1. Change along the surface of the earth. The value of g is not the same everywhere on the surface of the earth. It is because the shape of the earth is not exactly spherical. Therefore, the distances between different points on the surface of the earth and the center of the earth change from place to place. Since the earth rotates about its own axis, the earth is flatter at the poles and bulges at the equator. That is why the radius of the Earth is smallest at poles and largest at the equator. Therefore, the value of G is highest at the poles. It is 9.832 meter per second square. As we move from the poles towards the equator, the value of G decreases slowly. The value of G is lowest at the equator. It is 9.78 meter per second square. Now we will study the variation in value of G with change in height. 2. Change with height. As we go above the Earth's surface, the distance between that point and the Earth's center increases, due to which acceleration due to gravity decreases. If the height of the object from the surface of the Earth is very small as compared to the radius of the Earth, then the change in the value of G is negligible. For example, the radius of the Earth is 6,400 kilometers. If an aeroplane is flying at a height of 10 kilometers from the surface of the Earth, then its distance from the center of the Earth increases by 10 kilometers. The change in the value of acceleration due to gravity due to it is negligible. However, when we consider an artificial satellite orbiting the Earth, the change in the value of G due to the large change in the distance of the satellite from the center of the Earth has to be taken into account. In this table, some typical heights and the values of G at these heights are given. Come, let us now study the variation in value of G with change with depth. 3. Change with depth. If we go inside the Earth, the direction of gravitational force does not change, but the value of acceleration due to gravity changes. While going inside the Earth, the value of distance from the surface of the Earth, that is r, changes. As per the formula, if the value of r decreases, then the value of G should increase. But this is not so. The reason is that the part of the Earth which contributes towards the gravitational force felt by the object also decreases, which means that the value of capital M to be used in the equation of acceleration due to gravity also decreases. The combined result of change in the value of r and m is that the value of acceleration due to gravity decreases as one goes deep inside the Earth. The value of acceleration due to gravity at the center of the Earth is 0. The mass and radius of every planet and satellite is different. Hence, the value of acceleration due to gravity on their surfaces are different. And weight. Mass. Mass is the amount of matter present in the object. The SI unit of mass is kilogram. It is a scalar quantity. The mass of the object remains constant everywhere. As per Newton's first law, mass is the measure of an inertia of the object. Higher is the mass of the object, the higher its inertia. Weight. The weight of an object is defined as the force with which the Earth attracts the object. According to Newton's law of gravitation, the gravitational force F acting on the object of mass small m is equal to universal gravitational constant capital G into mass of the Earth capital M into mass of the object small m upon radius of the Earth capital R square. This is equation 1. Here, capital G into capital M upon capital R square is equal to acceleration due to gravity small g. Substituting this value in equation 1, we get F is equal to small m into small g. This gravitational force is nothing but the weight. Therefore, W is equal to mg. This means that the weight of object having mass small m is mg. Since weight is the gravitational force acting on the object, the SI unit of weight is Newton. Also, the weight being a force is a vector quantity and its direction is towards the center of the earth. As we move above the surface of the earth, the value of acceleration due to gravity g decreases, and so the weight of an object also decreases. As the value of g is not same everywhere, the weight of an object changes from place to place, though its mass is constant everywhere. In daily life, we use weight for both mass and weight and measure the weight in kilograms, which is the unit of mass. But in science, when we say that Rajiv's weight is 75 kilograms, we mean Rajiv's mass. The gravitational force acting on the mass of 75 kilograms is the weight of Rajiv. As Rajiv's mass is 75 kilograms, his weight on the earth is F is equal to mass m into acceleration due to gravity g, which is equal to 75 into 9.8, which is equal to 735 newtons. The weight of mass 1 kilogram is equal to 1 into 9.8, which is equal to 9.8 newtons. Our weighing machines tell us the mass of objects. The two-scale balances in shops compare two weights, that is, two masses. Now it's time for a question-answer session. Suppose you are standing on a tall ladder. If your distance from the center of the earth is 2r, then what will be your weight? Come, let us find this out. Suppose your weight on the surface of the earth is W Newton and your weight while standing on the ladder is W1 Newton. Here, W is equal to small m into small g. Substituting the value of g in the above equation, W is equal to capital G into capital M into small m upon capital R square. Similarly, W1 is equal to small m into small g. Substituting the value of small g in the above equation, W1 is equal to capital G into capital M into small m upon 2r bracket square. Therefore, W1 is equal to 1 upon 4 into capital G into capital M into small m upon capital R square. Therefore, W1 is equal to 1 upon 4 into W. This means that your weight when you are standing on a ladder is 1/4 of your weight on the surface of the earth. Do you know? Gravitational waves. You must have surely observed that when a stone is dropped into water, waves are created on the surface of water. Similarly, when both the ends of a string are held in the hand and it is shaken, then waves are generated on the string. Light is also a type of wave called the electromagnetic wave. Gamma rays, X-rays, ultraviolet rays, infrared rays, microwave and radio waves are also different types of electromagnetic waves. Astronomical objects emit these waves. These waves are received by our instruments. All our knowledge about the universe has been obtained through these waves. Gravitational waves are a very different type of waves. They have been called the waves on the fabric of space-time. The existence of these waves was predicted by Einstein in 1916. These waves are very weak and thus it is very difficult to detect them. Scientists have constructed extremely sensitive instruments to detect the gravitational waves emitted by astronomical sources. Among these instruments, LIGO is the prominent one. LIGO stands for Laser Interferometric Gravitational Wave Observatory. After 100 years of Einstein's prediction, scientists detected these waves coming from an astronomical source. Indian scientists have contributed significantly in this discovery. This discovery has opened a new path to obtain information about the universe. Come, let us now solve some numerical examples based on this topic. Examples, Set 3. Example 1. If a person weighs 750 newtons on Earth, how much would be his weight on the Moon? Moon's mass is 1 upon 81 of that of the Earth, and its radius is 1 upon 3.7 of that of the Earth. Answer. Let us first note down the given information. Weight of person, WE, is equal to 750 newtons. The ratio of Earth's mass to the Moon's mass, that is, capital ME to capital MM, is equal to 81. The ratio of Earth's radius to the Moon's radius, that is, capital RE to capital RM, is equal to 3.7. Suppose the mass of the person is m kilogram. Thus, weight of the person on the Earth, that is WE, is equal to small m into small g. Therefore, 750 is equal to small m into capital G into capital ME upon capital RE square. Therefore, small m is equal to 750 into capital RE square upon capital G into capital ME. This is equation 1. From this value of mass of the person, we can calculate his weight on the Moon. Weight of the person on the Moon, that is, Wm, is equal to small m into capital G into capital MM upon capital RM square. Substituting equation 1 in the above equation, we get Wm is equal to 750 into capital RE square upon capital G into capital ME into capital G into capital MM upon capital RM square. Therefore, Wm is equal to 750 into capital RE square upon capital RM square into capital MM upon capital ME. Now substituting the given values in the above equation, Wm is equal to 750 into 3.7 square into 1 upon 81. Therefore, Wm is equal to 126.8 newtons. The weight on the Moon is nearly 1/6 of the weight on the Earth. The weight of an object on the Moon can be rewritten as mass of the object m into acceleration due to gravity gm. Here, gm is the acceleration due to gravity on the Moon. As we know that the mass of the object remains constant everywhere, this means that the acceleration due to gravity on the Moon is 1/6 of the acceleration due to gravity on the Earth. Come, let us now proceed.